Good evening and welcome to our session. Thank you. I'm Walter Isaacson. Welcome to our session on nanotechnology. And surely I can think of nothing more important, especially this week, than studying things like nanotechnology that hold the promise, we hope, and we'll be talking about it, to tackle one of the biggest issues of our time. And that, of course, is energy needs in a planet going through climate change. As you can see on a slide here, the world population in 1950 was about 2.5 billion. Today, in 2017, that number's almost tripled, close to 7.4 billion. And the predictions are that we'll add another 2 billion by 2050. And of course, climate change is one of the consequences of this growth. So the dilemma is, how do we power the planet without destroying the planet? Let's take a look at why nanotechnology is so promising. Let me do a quick show of hands. Do any of you, or how many of you, know what a engineered nanoparticle is? Okay, I now know because I had it explained to me many times backstage. It's a good line about Einstein when Chaim Weizmann was coming over. And they asked Weizmann, do you understand relativity? And he said, Einstein explained it to me many times on the ride over, and now I'm convinced he understands it. And that's the way I feel about nanotech. Well, so it's about 20% of you. That's pretty good, better than most rooms I've been in. How many of you have engineered nanoparticles with you tonight? Actually, yes, correct. Let's try that again. If you're wearing odor-free socks, which I don't think any of us are, or if you have chewing gum or gummy bears, but most importantly, if you have a cell phone, you have some engineered particles with you, engineered nanoparticles with you. So the cell phone is a perfect example of how nanotechnology is making our lives easier, more efficient, and usually safer. Let's look at the scale of a nanoparticle. This on the screen is what a nanoparticle looks like, right? Right. It looks like nothing. Yeah. Well, almost nothing. Take a single strand of hair between your thumb and your index finger, and a nanometer is approximately 50,000 to 100,000 times smaller than that. To give you a sense of nanotechnology's potential, the easiest way to describe it is to have you think about an element, a noble element like gold, for example. Take a gold coin. You can carry a gold coin in your pocket. It stays yellow and solid. It does not react to other objects, which is why it's called noble. It comes into, for example, if you have the piece of gold next to the chip on your credit card, it won't react. But if you were to reduce the gold coin, reduce it to a size smaller and smaller particles, they will start to change colors. And at a nanoscale, the elements start to react differently. With over 100,000 known elements in the only 100 known elements in the period. Let's put up the periodic table so I can get that right. 100 known elements in the periodic table. There are seemingly endless potential nanoparticles to be explored. To launch us into this evening's discussion about nanotechnology's promise to both meet the existing and growing energy demands without further warming up the planet, here's a look back at the carbon conundrum. Carbon's a tricky element. It is essential to the planet Earth, yet its impact on the climate has become one of the biggest threats to the planet's survival. Does carbon have the power to save itself?
How is it that carbon, the building block of life, can be so essential, yet its impact on the climate be so harmful to life on Earth? Even the most complex molecules that make up life, nature, and the Earth contain carbon as a major component. animals and humans wouldn't exist without carbon. It is also abundant in the atmosphere in the form of carbon dioxide, and it is trapped in the earth as rocks and fossil fuels. This continuous cycle of life, where carbon travels from the atmosphere into the oceans, organisms, and the earth, and oxygen is released, is one of the ways this planet is unique. For millions of years, human ancestors ate plants for their primary source of fuel, and they reached a turning point when they learned how to make fire and use its energy. As animals were domesticated, beasts of burden became an important part of the workforce. The invention of sails opened up trade, travel, and exploration between civilizations. Water wheels powered mills, ironworks, and other industries. Europeans popularized the use of windmills to grind grains and spices and saw wood by the 1600s. And innovation in renewable energy continued through the 18th and 19th centuries. But these inventions proved more fantastical than practical. The game changer was Thomas Newcomen, who disrupted this gradual evolution of energy technologies when he invented the steam engine in 1712. But it was James Watt who made it more powerful and efficient and lowered the cost of energy. This paved the way for the Industrial Revolution and led to the invention of the internal combustion engine. As progress and prosperity continued, the infrastructure grew into highways, coal plants, oil and gas, nuclear reactors, and hydroelectric dams, which promoted the rise of electricity and transportation throughout the 20th century. To give a sense of scale, in roughly 350 years, mobility alone went from 1 horse-powering transportation to the equivalent of an 87,000 horsepower jet. Populations have grown from 2.5 billion in 1950 to 7.4 billion in 2017, further driving up the demand for energy and carbon in the atmosphere. And this is how carbon, an essential component of life, became part of one of the biggest threats to life on Earth. So, what are the stakes? As it stands, since the beginning of the Industrial Revolution, the planet has warmed up by 0.8 degrees Celsius. Continuing with business as usual, it is predicted that by the end of this century, average global temperatures will rise by 4 degrees Celsius. Some would ask, should we keep the Earth's carbon in the ground to save the environment? Or use it to continue growing and take our chances? Business as usual does not factor in the potential for human innovation to come up with better options. The combustion engine was a game changer. The transition from wood to coal led to the Industrial Revolution. And carbon may be poised to disrupt the power structure once again. Drilling down to the tiniest of scale, nanoscientists and engineers are now harnessing the unique properties of carbon molecules to find powerful clean energy solutions and meet the energy demands of exploding populations on a warming planet.
We have with us tonight 3 top nanoscientists and environmentalists who are working on cutting-edge and groundbreaking technologies to help mitigate our carbon dilemma. As we discuss the worldwide race to come up with alternative energy applications, We'll also take a look at any possible implications that nanoparticles may hold when they're released into the environment as part of the process. We'll also be taking your questions. You'll have to pull out your Nanotech engineered phone and tweet your questions to hashtag WSF17. That's like in World Science Festival 2017, hashtag WSF17. Our first guest holds a UC presidential chair and is a distinguished professor of chemistry and biochemistry and of materials science and engineering at UCLA. He served as the director of the California Nanotechnology Institute and is the founding editor-in-chief of the leading nanoscience journal, ACS Nano. ACS, what's that for?
American Chemical Society.
Yes, great. Please welcome Paul S. Weiss. Our next guest is a distinguished university professor and trustee chair of materials science and engineering at Drexel University, founder director of the A.J. Drexel Nanomaterials Institute and associate editor of the ACS Nano. Please welcome Yury Gogotsi. And also joining us is a distinguished professor of chemical engineering, the founder and director of this CUNY Energy Institute. The Energy Institute has incubated several spin-outs, notably Urban Electric Power, and he's chairman of the board. Please welcome Sanjoy Banerjee. Well, this isn't a new concept addressing climate change. We've been working on it for a while, so I'm going to start with you, if I may, Professor Weiss. Give us a sense of the size of this challenge.
Well, we have a long way to go in terms of improving efficiency, making devices that hold more energy, that harvest or capture energy more efficiently. We're really at the start of a race to see which technologies will carry the day and hopefully carry us forward safely in the future.
But what are the major energy sectors you see helping us do that?
Right, so there, in collection of energy, for instance, there's solar. We could be much more efficient in terms of how we harvest energy there. We're well on the way in terms of trying different materials. There's some strategies that haven't been applied at all yet, capturing wave energy based on converting the motion and energy in waves into electricity.
Explain that one. That's a fun one.
Right. So in your cell phone, when it makes a noise, or your bathroom scale, there are materials that change the pressure into voltages, and that's how your scale weighs you. And you can use that same technology when waves put a stress on a material to generate electricity. And unlike, say, wind or solar, waves continue over time, and we can imagine floating or having slightly submerged structures that over a small fraction of the area of the ocean collect enough energy to provide power.
So that's sort of a future vision of what renewable energy could be. But start with this now. Where are we on renewables? About what percentage of the world's energy is renewable?
Well, a small and growing percentage comes from solar. We have a part, I think we have something up here, right? So let's have a look at this. I mean, you can read the numbers. Let's look at what's going to happen in the future. So we have increasingly inexpensive natural gas, and we expect that to grow in the near term. We expect certainly less coal. It's basically costly, wasteful, and polluting, despite where we are politically. Yeah. In the U.S., other fossil fuels we expect to go down and will be an energy exporter over time. And then energy sources like solar are increasing. We've had a jump ahead in terms of decreasing cost due to national policies in the U.S., Germany, China. Wind power, for instance, has great potential to grow. Denmark's going to go from about 40% wind now to about 85% in a few years. In a small country that's technologically advanced like that, policy decisions can drive those changes.
Well, which ones are growing the fastest now?
I think, while solar is a small fraction now, I think that's growing the fastest. If I remember
But
correctly,
on a small
job growth.
base, yeah.
The intercept, the starting point is low, but the potential remains high.
And it's solar, wind. Tell me about the cost curve there. Which ones are coming down fastest?
Well, they're both. So solar for funny reasons related to production, the cost of the materials is extremely low compared to what was expected.
The funny reasons are China allowing a lot of
different
production?
provinces in China had to compete to stay in the game according to their rules, and that made it tough for other countries to keep up production of silicon for solar. Wind, I mean, we haven't come close to exhausting the capacity to place wind farms, and we see those around where I live in Southern California, off coastlines and other places in the world. As I said, the blue energy hasn't really started yet. Hydroelectric and nuclear, we have facilities in place, and those, if they were to grow, would grow only rather slowly. The infrastructure costs are so high.
Yeah, no, I was going to drill down a bit on nuclear.
Sure.
What, the infrastructure costs will prevent us from growing nuclear?
Well, infrastructure and, again, policy, right? It's hard right now to build a nuclear reactor. Some
Is
are
that
being
good
shut
policy
down.
in your mind or bad?
It's policy. It's, some people will be on one side of it and some people will be on another, but it would be hard to build reactors fast enough to keep up with demand. And so almost certainly we're going to end up taking other approaches.
Yeah. So there's no leap in technology on nuclear that might make it easier, like small nuclear?
We don't invest a lot into trying to come up with solutions that are nuclear,
the
and
Bill
so that
Gates one,
that's again, that's a policy decision about where we place our bets for the future. If we don't put effort into research that promotes those technologies, then they won't develop.
Let me turn, if I may, to Sanjay. Why is nanotechnology such a promising science, when it comes to energy development?
So one of the areas which I think is sort of the Achilles heel, if you wish, of renewables like solar and wind is the fact that the sun doesn't shine all the time and the wind doesn't blow. So you have to have some form of storage in order to be able to utilize these types of technologies. And in the energy storage area, which is absolutely vital, nanotechnology is likely to play a key role.
Let me translate real quick.
Yeah.
By storage, do you mean batteries, or are there all sorts of other storage?
Well, I think that I mean primarily storage of electricity. And of course, you could also store sunlight by breaking water into hydrogen and then storing the hydrogen and maybe mixing it with natural gas to improve the calorific value. There are also ways where you could take sunlight, for example, and make it into liquid fuels. So I'm leaving that aside for the moment. I mean, there are applications of nanotechnology in all of those things. But focusing primarily on electricity storage, batteries, capacitors, and things like that, which can be distributed close to the point of use so that the losses that come from transmission, distribution, and so on are minimized. And
well, let's look at some of these things. How important is location? Are we really going to decentralize and allow power sources to be on my roof?
well, I don't know if it'll be on your roof. I would like to have it on my roof.
My roof in New Orleans, yes, it is.
Yeah. But yes, I think that if you had the area, roof area, of course, but I'm looking at it a little bit differently. In many parts of the world, for example, let's take India as an example, I think it's around 35% of the villages don't have electricity. And to bring transmission lines and so on, I might be wrong with that percentage, is very difficult. That requires a whole enormous infrastructure to lay these lines.
So what
and so on.
advantages would renewables have to focus on that issue?
So let's look at that. If you had local renewables, say solar or biomass or wind, you could leapfrog the transmission distribution system and have a system where you store it locally and use it when needed. I'll give you a simple example. For example, in India, you have a set of solar panels for a village, and people go charge their batteries and take it home and use it. Or the battery gets dropped off to their house for a small payment. Every evening, they use it for their lights or whatever. In the morning, the battery is collected and brought back to the solar charging station. So simple things like that.
So what would this do to the grid? Would you be able to leapfrog having a complex grid, or do you have to change the grid to make it work?
Well, the idea is that it's like a cell phone, right? Yeah. You want to leapfrog the landlines if you can. Right. So that's the idea.
And you mentioned biomass. Explain how that's different from biofuel, just because I know we're going to be talking about it some.
Okay, so I think when I talk about biomass, I include in it biofuels. But biofuels are only one way to use biomass. You can certainly take cellulose, cut the sugars if you can. You'd have to have a very clever enzyme to do that, and then be able to, ferment the sugars and make alcohol, which hopefully you don't drink, but you actually use in cars. And then...
well, we're already doing that, right?
Yeah, but we're not cutting cellulose. It's a real trick to do that. Okay, I think that's really a problem. The second area is just either using it directly by burning wood or whatever, or you can also have biogas made from, just letting this rot.
And that includes ethanol,
Yeah.
right?
Well, yes. Biogas and ethanol, two different things.
Right, but I was wondering if you're including that.
Yeah. So in a sense, biofuels are quite widely produced already, and people also burn wood, a lot of wood.
Well, you've mentioned burning wood, which obviously is renewable. Intuitively, that doesn't address the issue of climate change to me, or putting carbon into the atmosphere.
Not in the short term. But actually, as you know, wood fixes carbon. So if you look at it, there's a certain time lag. But one of the best ways to fix carbon is to grow more forests. Right? You make more wood.
Wouldn't that be better to grow more forests without burning as opposed to with burning?
I completely agree with you.
Okay, I just want to make sure I wasn't missing something there.
Yeah.
So we're not, sometimes I say this not just as a joke, but we keep talking about renewables. There are good renewables and bad renewables when it comes to climate change. Is that right?
Right.
Okay. Yury, if I may, why is the constant reinvention of materials so important to the renewable energy solution? And I'll use renewable there, but you can correct it and say carbon-free if you want.
One of the reasons is that we cannot move far beyond the current technologies without materials. You're just talking about cell phone being a good example of nanotechnology. So it was enabled by new materials. For example, no one could imagine probably 20, 30 years ago that a very thin glass, which we all considered to be one of the most brittle materials, would be able to be on screens on every cell phone. And the power of big computers can be squeezed into a small box that everyone probably in this room carries in a pocket. Here, very similar things happen with renewables, with energy storage, with energy generation. We need new catalysts, for example, to split water using sunlight and store hydrogen. We need new materials to make batteries or, in general, energy storage devices. And moreover, there are many more sources of energy that we don't use. For example, like triboelectricity. Paul mentioned blue energy, energy of waves, which is huge, can be collected. But each of us, when we move, we produce some charges, electrostatic charges. And we get usually irritated where our, say, pants stick to our legs because of static electricity. But we can collect it and charge our cell phones. However, we need new materials capable of doing this. And that's why, really, if we want to move forward to really groundbreaking, revolutionary technologies, we need new materials.
How important is the element of carbon to the creation of those new materials?
Well, we're all made of carbon. Wood we burn made of carbon. Coal we burn made of carbon. And it's a much better way. Instead of burning coal, burning oil, burning gas, take carbon out of them and make it into new materials. For example, for storing electrical energy from renewable sources. And carbon is just simply the most versatile material. It comes as the hardest materials known to us, diamond. And soft, electrically conductive graphite. Diamond is transparent. Graphite has metallic luster because it conducts electricity. Strongest fibers known to us are carbon nanotubes. So it's just a very versatile element and also the most abundant. If we stop burning oil, if we stop burning coal, we will have plenty of carbon to design a world of carbon materials.
Why is carbon so versatile? And if it is, why can't we control it better?
Well, again, versatile things are complex. And I don't want to go too deep into science and chemistry, but many people in this room probably remember from high school chemistry that carbon atoms can rehybridize different ways. They can form linear structure, planar like a graphene, and can form carbon nanotubes that you can see on screen now. And this is what allows us to make carbons with different properties. For example, you can see a carbon nanotube, which is 100,000 times thinner than a human hair. But this is the strongest fiber in tension that we know today.
So what do nanotubes do? Or what do we want them to do?
Well, we want to do many things. They can become, for example, cables that will be much lighter than steel or aluminum and can conduct electricity. They can make much faster electronic devices. But what is interesting, today the most important bulk application in nanotubes is additive to batteries. Just in China alone, about 400 tons of nanotubes are produced every year to add conductivity to batteries, make our batteries charging faster and working, living longer.
What else do we need to do to improve battery technology?
Well, we need really redesign the batteries. Today, battery is consisting of chunks of materials in cathode, anode, where ions move very slowly to store charges. It's very similar, actually, to traffic in New York City. I was getting through this traffic today in early afternoon. Luckily, my son was driving. I was able to do something useful. But this traffic, I think, drives anyone crazy. But before that, we were moving on a highway for about an hour with a high speed. So when we have current materials in lithium-ion batteries, this is like traffic in New York for ions. It takes a long time to get through. That's why it takes you about 2 hours to charge your computer battery. If we have nanomaterials where every ion has its nanochannels, like a nanotube or between graphene sheet and other carbon structure, they can move much faster. And you want to be able to charge your cell phone battery within minutes, and it's doable already today. But we also want to be able to charge electric car battery, for example, what Elon Musk promised, chairman of Tesla, within 5 to 10 minutes, just with the same time we fuel a tank of our car. And this is simply impossible without nanotechnology.
This is the New Jersey Turnpike theory of battery design. But help me understand it. It would charge faster because you'd have many more conduits for the ions.
Exactly, because with nanotechnology and nanotube, we can make conduits for ions very quickly go in, and the same carbon layers or nanotubes or other new materials will conduct electrons. So electrons go one lane, ions go another lane, and both can move faster.
Why aren't we doing this? What's the holdup?
There are a few things.
What's the easy pass we need to get through this
First,
lane?
we need to develop those solutions. That's what scientists do.
Yeah.
Second, we need industry to take on this because there are many great engineering scientific solutions, but when you have established industry, multi-billion-dollar industry making lead-acid battery, making lithium-ion batteries, it's very difficult to leapfrog it and get to a new technology which may
But
be
we're
better.
very good these days at disruptive technologies, leapfrogging, knocking old industries off the map. It would seem to me whoever creates a quick battery technology, that I would want to invest.
It is happening. I know there is a company in Israel that already making these chargers, which are we call supercapacitors, that can charge your cell phone within 5 minutes. So it's already existing technology here. It just is coming step by step to a larger scale.
Let's go to a bigger scale, which is airplanes. How's it being used in airplanes? I think we have an animation of this. Maybe not.
I
Go
don't
ahead.
see animation coming,
Yeah.
but in
We're talking about a carbon airplane is what I was trying to
well, again, airplanes need to become lighter. Lighter is the airplane, less fuel is used. By the way, Boeing 787 Dreamliner is already made more than 50% of composite materials, which use carbon fibers. And in this case, for example, what you see right now, it's electromagnetic shielding sheet. Instead of copper wires, we can use a coating which is at least 10 times thinner than a human hair and will provide the same protection as shielding here. So if you use these lighter materials, we will consume less energy. And this, again, important for the entire discussion. One way is to produce more energy, produce energy from clean sources. The other way is consume less by smarter way of using it.
Before we move on to the next section, I was wondering if either of you wanted to chime in on some of the things we've talked about.
Yeah, so really it comes down to 3 parts. There's collection, there's storage, and there's efficiency. And in each of those, nano has a role to play. We have laboratory demonstrations of many possibilities, and we can also calculate how far could we go if we figured out how to make these nanostructured materials that not only have much higher efficiency, but also we're after stability. In many cases, the bulk materials might be able to do something once, but then they fall apart because of structural changes, like lithium-ion batteries. They're better solutions that don't really work.
Dreamliner,
Yeah, that don't really
airplane.
work yet. Not that exact battery, but
Yeah.
yeah, there are others that could have much higher capacity. We know it's possible. We just haven't figured out yet how to accommodate mechanical changes, for instance, that accompany the function of that battery, and they fall apart
And
very
real
quickly.
quickly, because I realize we may be leaping ahead of some of our understanding. When you say nanotechnology, are you talking about a scientist manipulating atoms in a material to create new materials, or what do you mean?
Well, one can do that. That's how I started my career in nanoscience. But that's thanks very much. But that's not really a solution to go to the grand scale of
Well, I
batteries
just want a
and so
good
forth.
definition of nanotech.
Oh, okay. Sorry. Yeah. So think of the smallest scales being chemistry, where we react atoms and molecules together to build up structures. It's how all the molecules in us are made. And so we can go beyond that and put molecules and other structures together. That's sort of bottom-up version of nanotechnology. The other is the top-down, which is a direct descendant of stone and wood carving that we've done as humans for centuries, only now we're doing it in materials like silicon, where we start with a big crystal in a semiconductor foundry that's going to make computer chips. We cut it up first, and then we do simple chemical reactions that can turn it into the metal traces that connect the devices together, the insulators that prevent them from talking to each other when we don't want them to, and then we do simple reactions that make the transistors and the memory and the logic that turn into the several billion devices on a single chip that we use in our computers and our cell phones now.
And do you think that will allow us to keep with some iteration of Moore's law?
It keeps going. We keep saying it's going to end, and yet we've stayed on track so far through incredible cleverness on the part of scientists and engineers.
Sanjay, let me turn to you because I want to look at energy technologies that have slowed down and not yet scaled up. What makes it difficult for renewables to compete with fossil fuels?
So any energy technology has a long time constant penetrating, and I think Yury gave the example that even if something is invented to actually disrupt something in the energy sector takes a long time. And in particular, he gave the example of, say, lead-acid batteries. This is almost a century-old technology which is highly optimized. It's a huge industry. You know, even if you bring in a new technology, the activation energy to get over that hump and be able to make it work is enormous. And so renewables face some of those same problems in the sense that, you know, oil, gas, natural gas have been around for a long time. They displaced, you know, other technologies, you know, like hydro in some sense over a long period of time. It'll be a while. I think it's sort of like the time constant is roughly 50 years. So I think between when renewables become economically attractive and when they actually are able to widely displace fossil fuels, that'll probably be something like 25 to 50 years.
Are we going backwards a bit, perhaps because unconventional sources of natural gas and the ability like fracking to extract it have made natural gas so much cheaper?
Well, in certain parts of the world, you're absolutely right, because you have to be able to compete economically, otherwise it's not going to happen. The price of solar, for example, is coming down rapidly, and even wind is already relatively low. So it's relatively competitive in areas where there's lots of wind and sun. But in other areas, it's not. Natural gas really is the competition right now. But there are vast areas in the world with high energy demand where that's not true. That includes China and India. And there, I think...
China and India do not have the deposits of natural gas, or they aren't using the industry to extract it?
They have, I mean, China has shale, but it's not near water. So it's not easy to extract that. It can be done, but it's difficult. India does have some offshore resources, but it's not really of the same nature as here. So there's a shortage there. And you could probably see things like renewables coming on faster in these areas where the natural gas supply is lower and the price is higher. It's difficult to see that when the natural gas price is as low as it's today, you know, unless it's mandated in some way, like California or wherever.
Or it's mandated by putting a tax on carbon. Would that be the easier way to do it?
You could do that, yeah.
And you say that gas is not available in some places or can't be extracted that easily. Would liquefying natural gas and allowing it to be exported, would that change the cost equation and perhaps even hurt the growth of renewables?
It could, though there's a cost associated with, you know, liquefying it and regassing it. So a regas station costs several $1 billion to put in. So it's not without its costs for transportation.
And this is sort of for everybody here. I've noticed both in my pre-reads, the questions and all, we use the word renewables as all good. I mean, that's cool, it's renewable. But as we said with burning wood, which is a renewable, there's a difference, or is there much of a difference between renewable sources and clean energy sources?
Well, there's the issue of efficiency again. So burning is relatively inefficient. You're going to get the energy out by some further secondary process, whereas if we come up with a chemistry or biology that takes cellulose directly and is able to produce energy for us,
in other words, take a piece of wood and make energy out of it without burning it.
Take it apart chemically and use the energy that's stored in those parts that the tree created or some other plant, and use them more directly to produce energy for chemist, oxidation and burning are the same thing, but you can do that much more efficiently the way some bacteria do it. And so,
And by more efficiently, you mean you put less carbon into the atmosphere?
well, you get more energy out for the carbon you use, so effectively that's putting less CO2 out into the environment. And so that's really, I'm not sure people would call it a branch of nanotechnology, but there's an associated biology of teaching bacteria to do what we'd like them to do, whether it's create a chemical that we could use as a fuel or create a drug through using the enzymes that they either have or could have if we reprogram them. And so there are strategies both to treat cellulose and other molecules that are present in abundance, or also to take algae and have them collect sunlight and produce fuels through adding some biological capabilities to the repertoire they had to begin with.
And would this be a significant contributor to preventing climate change?
It could be. Again, we have a potential portfolio, and we're very much at the start, and so we can choose where we invest our research money to advance those technologies and see how they'll compete.
Yury, you were about to say something.
I just wanted to add to this that I think in all this portfolio of possible technologies, there is a really large role that government and regulations can play. And there should be social request. I'm old enough to remember smell of the cities, and sometimes I go to countries that still use cars with no catalyst. There was no profit for any car company. We all pay more for cars because there is a catalyst here. Gasoline became more expensive because there is no lead in the fuel, because it poisons catalyst. But it's a different air. We breathe air which is really so clean and enjoyable to breathe compared to places you go in some developing countries when people still use ethylated fuels and have no catalyst. Same, many of the cities were so polluted and smoked by chemical metallurgy industry that it was hard to breathe. I actually studied metallurgical engineering in Ukraine, and as a student, I spent a month on a metallurgical plant. A river was floating by was red. Air was sometimes yellow, sometimes gray. And coming back, if you wear a white shirt, you would basically have it all covered by dust in the air. And regulations changed. Yes, certain things become more expensive, but the price of better health, better air, quality of life is important. So I think without really push from government, without regulations, very difficult to break this cycle if we all need to look. It's cheaper to burn coal. Let's burn it. And China is actually doing it because some of the most polluted big cities are now in China, like Beijing.
Moving away to
regulation,
cleaner,
right. For example, they switch all school buses to electrical buses. Right. Electrical transportation, supercapacitor, batteries, hybrid buses being introduced in many, many cities here. So I think this is where central government or state government really need to play
an argument for staying in the Paris Climate Accord.
Unfortunately, we made a step in the opposite direction recently.
Mm-hmm. Yeah. Well, Los Angeles in the 70s was like what Yury described, and through a series of steps, including having special mixtures for gas, for which we pay more, we can now breathe with 3 times as many cars on the road. So we have a lot of ties to Beijing, where they have a similar basin that collects pollution and makes it sometimes impossible to breathe, and you can taste it on your tongue. There we have people who go back and forth and try and learn from what we did over the last 40 years to make,
I can remember the dramatic change.
It's
pretty quick in Los Angeles.
That's right,
over
and
a
still
12-year
going.
period.
We're still taking the most.
I remember when it was all smog.
Yeah, what's left in terms of what damages there, we still are taking those out, and that's something. Well, people have to measure what's in Beijing. That's the start of it, but they'll institute, I think, some of those same strategies.
But one of the things Yury talked about and all is doing it through regulation, which is okay if you can have a government that's willing to do it that way. Another way to do it is just to put a price on what you don't want to have exist, like put a price on carbon.
But you
if
need
you
a
want.
government
I
to
think
do
that's
it.
policy. That's
You need a government to do
Right,
it.
but it's a policy question, and I know we're not here to change governments in the United States on this stage. That's happening outside. I think they're doing a protest for that. But let me ask it in a scientific way. If you were going to try to incent a development of industries, such as clean industries, would the simplest way to do it be not regulation, but just saying, here's a blanket price on carbon? Would that help science progress better?
That's a policy question.
Oh,
I guess.
all right.
Yeah. But we can.
Yeah.
I mean, let's back it up a bit. What we can do is we can invest in research that's going to advance technologies that could play significant roles. And not only can we watch those, we can place our bets where they'll have the most effect. So whether
Can
it's
I
carbon
just-
tax, some other policy, there's a way to.
Interject something. I was at a very interesting discussion once between John Podesta at that time, who
He
was
still is John Podesta,
Yes.
but despite what happened to him,
and Steve
still a
Chu.
good man.
Steve Chu was then the Secretary for Energy. And what was interesting is they were quite polarized in some sense. That John Podesta thought that the solutions came to climate change through policy, and Steve thought it would come through technology. You see, so I mean, they were sort of polarized. But I think
Well, I
there's
was
some,
actually asking the Steve Chu question
Yeah.
because when he was energy secretary, he said, if you're going to make it come through science, just put a price on things that you don't want.
right. But I think there's some intermediate position, like everything else.
I think it's a
Yeah,
combination.
you
of
do
both.
need regulation, I do think. It's
Let me
not
go
just
back to
price.
batteries,
Yeah.
your specialty. What is it about the technology? Let's leave aside the nanotubes, which we've now solved with the New Jersey Turnpike model of battery charging. But what about the storage capacity of batteries that seems to me, maybe I'm wrong, everything else is growing and doing well in leaps and bounds, but the storage capacity of batteries hasn't gotten much better. Is that a lithium-ion question? I know we had a slide we were going to show.
It'll come sometime, but
Yeah.
yeah, I think the issue really is how are you storing energy there? You're storing it through chemical bonds in
You can
some way.
refer to that if you want.
Oh, okay. So we have this is actually an example to show you the time constant associated with even a very major scientific discovery, permeating through. And you can see that the discovery was made in the 70s and 80s, but before it became a reality, it took another, sort of 10, 15 years. And
I'm sorry, what was the discovery? That lithium?
the fact that you could intercalate, intercalation cathodes there. And what you see there, that the first commercialization of this came really due to Sony, who was able to put together the lithium cobalt oxide cathodes. And
The
with
discovery was made in the US, but no one cared.
Well, there was Oxford, US, and so on. But nonetheless, look at the price changes over time. You can see that within about 20 years, the price came down by a factor of almost 10. And now it's, of course, beginning to asymptote in some sense. But this
Is there another leap that's going to happen? It's not a leap, because there is no leap on that chart. But is there another inflection point that's going to happen? Like,
well,
we'll discover something?
This enabled your personal electronics,
Right.
essentially. Whether this will enable an electric vehicle or electricity storage in the grid is a different matter, because.
But you talked about the intercalation tube, cathodes that you use.
Right.
That happened then that caused this, right? Is there some other big advance that you would hope for?
Yeah, well, one is this sort of superhighways he's talking about in batteries,
Yeah.
but that would be
Yeah,
one.
that'll make the
certainly.
capacity keep going up. It'll be, like our laptops, we pay about the same for them every time we replace them. It's just they do that much more each time.
I'm
So-
just hoping for quantum effects.
Well, could you have, well, Right.
Maybe, but one of the way, for example, those are lithium batteries. Lithium has one electron to give away.
Right.
So if we can get magnesium or aluminum, inexpensive elements, inexpensive materials, which can give 2 electrons per magnesium atom, 3 per aluminum atoms, we may potentially have battery capable to store more. But we're still trying to work out scientific problems and challenges that prevent us from using
Trying to get
those
aluminum
elements.
to give up its I mean, it's
3 electrons
three,
per
I mean,
atom.
and
So
so that's a real nanotech problem, is extracting an electron from aluminum, right?
That'll
Well, but zinc does.
All else being the same, you get triple
Zinc is
the
solution.
capacity.
And you have a much better, this is getting back to policy, but lithium is a policy problem too, since it comes from places that are harder to get.
Well, it's cobalt, which is more of the problem, actually.
Yeah, well, cobalt. Let me Paul. What other liquid? I mean, we need some liquid fuels, right, for cars, whatever. I know we'll have electric or whatever. What other things have a potential of scaling up?
Well, it's really how we make those fuels.
Yeah.
So if we are able to start from plants and produce them efficiently, or have algae that collects sunlight, then we have a shot at making those fuels on our own without, digging up oil or burning coal. People are trying to make the bugs, as I was describing earlier, that you could put liquids down pipes so that we could distribute those, in analogy to what we're able to do now.
You have a chart up there, and I was just wondering what issues you have making those better. I mean, it's just doesn't seem to be scaling up that well.
Well, as I mentioned, it's fair. Solar, we know, is going to be going up. Wood, there are more efficient ways to use it than we do now, and that would increase its contribution without increasing the amount of it we actually had to make and transport. Oh, you lost your mic.
Yeah.
There's some things that haven't hit yet. Wind, we know, is going to keep growing, and it's really just a matter of production and policy to put it in place.
How important is the grid system to allowing us to decentralize?
So the grid will be what happens to the grid will be incredibly interesting. Right now, we depend upon central facilities for our power, but if we all have those tiles on our roof when it's sunny out.
I wanted the ones where you get your static electricity off your trousers.
Yeah, you're probably not going to power your house with that, but you may
Okay.
be able to recharge your phone. So, but the grid then becomes more interactive, and the question is, if the companies that are producing power and paying for the grid now have a smaller contribution to the energy we produce, who's going to pay for the grid? And again, there's going to be a policy change.
In
and
other
the
words, how do
arguments-
we get the electrical utility companies to allow this?
Well, the argument is, right, there will end up being some sharing of the cost of the infrastructure on which we depend when we don't have our own power or we're trying to sell it. And those arguments are already going on about how we'll be supporting
In other words,
that
when I
structure.
want to sell electricity back to the grid,
Right, you may end up paying in part for the cost of the grid. Yeah, and then
that sounds logical in a way.
It does, but then, of course, how much?
How
It's going to
much,
be
yeah.
the devil's in the details, as they say. And even off the grid, as Sanjoy was saying earlier, we have experiments going on where these communities on islands or above the Arctic Circle that are off the grid. And so, the Arctic ones are kind of interesting because they have solar power available only part of the year, and so they need storage in some form or another. And those are really laboratories for how we might consider distributed grid.
If you have a distributed grid like you just talked about, or a crowdsourced grid, even, how much would that do to help us consume less energy or at least emit less carbon?
Well, I think that the transmission issue is maybe the biggest
Big one.
one. We lose, I think it's 30% of the power just in transmission from the power.
Yeah, of that order.
Yeah.
So in other
And
words,
so
we're
you can-
talking about a potential, we won't say 30%, but at least a 20% leap if you could get rid of the transmission.
Whatever fraction doesn't use that transmission. So
Right.
if it's just residential, you had that up before. But if
Yeah.
it's just residential, that's a fairly small fraction. A factory, may still need to be powered by a central facility if they don't have their own. And yeah, go
Yeah,
ahead.
Yury, and then,
Yeah.
I think there is another very important aspect of this. It's energy security. How many years ago did you have a major blackout in New York? 6, 7?
You're not counting Superstorm Sandy, but yeah.
Right. Yes, after Sandy.
Okay.
I hear. Imagine now 2 weeks without electricity. Terrorist act, natural disaster like Sandy or something else here. Without being able to withdraw money from credit card, without being able to charge computer, elevator stop, everything here. Life pretty much stopped. This country can be destroyed staying 2 weeks without electricity. And the only way to do it to decentralize the grid. Then it will become stable for most of the country. When we can produce electricity on the roof of every single family home in America, when we can store it, when we can produce enough electricity to power a cell phone, just simply by walking, by having solar everywhere. So I think there is this aspect which is also very, very
So
important.
you could save up to 20% of the energy, but you could also make it so much safer. Just like the model of the internet, it doesn't go down as easily because
Exactly.
it's totally distributed or
Exactly.
decentralized. And why aren't we doing that? What's the holdup? Oh, you're going to say that's a policy.
Well, I
issue.
don't want to talk about utilities
you know
companies.
that New York has actually many microgrids actually set up in the
Are those
city.
crowdsourced? Or are those set up by
it's
Con Ed?
Con
or
Ed,
whom?
but there are many microgrids. So some of the security he's talking about.
Why is it that, I'll pick New York,
Yeah.
so little of the energy used in New York is generated on a very local scale? I mean, in other places, people have solar panels, everything else. I don't know of any buildings in New York that try to be solar powered. Is that impossible to do in a city?
Not really. In fact, I gave a talk once which related to this. There is a lot of roof area, not in Manhattan maybe, but in the 5 boroughs. So you could have some significant part of our energy budget being made come from the
And
roof.
what's stopping that, or what's hindering that?
Well, maybe regulatory structures and stuff. But remember that a lot of our energy use is for heating oil or heating. So it's not necessarily just electricity.
I assume solar could do a lot of heating.
But in winter, it's a little hard.
Okay.
I mean, yeah.
You were talking about graphene, I think, a minute ago. Do you want to, I mean, what is it? How's it used? Is that going to help us?
Well, again, graphene is one of simply the most popular nowadays materials. It's a single sheet of carbon. So basically, if you take graphite, you write it with a pencil, with a graphite lead, and you leave thin flakes of graphene on the surface. So it's a very common material. But when separated from a large chunk of carbon into atomically thin layer, it has wonderful properties. It's highly conductive electrically, it's light, it's strong, so you can make structural materials, you can make a battery. It can conduct electricity, so it can become battery materials or supercapacitor material, which is a kind of battery on steroids that can work faster. And from graphene, you can, as you see from this picture on screen right now, you can roll it in a seamless nanotube, you can stack it into graphite, or you can make spherical particles, fullerenes that use, for example, to produce solar energy. So it's a kind of a building block. And I think actually you asked Paul about definition of nanotechnology. I think nanotechnology is much designing with very, very small particles, with atomically thin layers, with atomically thin
Inventing
tube.
new particles.
Right.
too, or
And of course, you know,
materials.
it's like a building block. We need a lot of different building blocks, but then we can construct materials, whether it's a battery or material for a new super light, super strong jetliner from these structures. And
Since
this is
I'm
what
on
Nano
the
does.
Upper West Side here, and there are lots of worry committees on it about unintended consequences, like of genetically modified food. You know, people would worry about that. What are the unintended consequences we should worry about?
So we have a whole panel on that tomorrow.
Oh,
Thanks
okay.
thanks for putting in a plug for that one.
Please
It's
come
at
by
11.
tomorrow
I
if you're on
forget
the
where it
Worry
is. It's not
Committee.
on this stage,
Yeah.
but
Yeah.
feel free everyone to come to that one. But so there's this incredible diversity in nanomaterials, and the way we've regulated those so far has been to treat them like chemicals. And it turns out there are not enough animals, and there's not enough money on the planet to do conventional testing of nanomaterials. So a new strategy we've adopted in California, the US, EU, and China, based on very current research, is to categorize materials into this class of materials appears to be safe in all these ways. Go ahead and start commercialization with those. There are other materials where we see some sign that we need to investigate further, and usually when we do those first tests, there's a mixture. And so the two things we can do are separate the mixtures to figure out which of the components are the ones that are raising red flags, and then also to do more detailed testing. And then there are others that we know have significant consequences, not all of which are bad.
Give me an example of a consequence,
Okay,
a bad
so-
consequence.
Well, look, the nanoscale is the scale of function in biology. And that's a good thing and a bad thing. It means we can interact with biological systems. We can try and treat tumors or diseases or understand how the brain works by connecting nano devices to neurons and listen to them talking to each other. On the other hand, a virus is a nanoparticle, and it can have significant consequences for us. One can make nanomaterials that include, elements that can interact with our cells. So,
Let me get to the big issue of the week, because all of this has been about climate and trying to reduce the amount of carbon that we're emitting. From a scientific perspective, how bad was pulling out of Paris? Would be pulling out of Paris?
so for me, maybe I'll start.
Go.
I think that individuals and companies and cities and states are not going to pull back. And so the question is, what fraction? And so we're not 100% going to stop what we were already doing, but it's really up to all of us and the organizations we're in and the cities and states we're in to carry forward. And I'm in California and proud that we'll push on our own if we have to, but I don't think we're going to be on our own. I saw at least 60 mayors of major cities said that they'll continue.
Can you calculate, say 60 mayors do that, but West Virginia decides to burn coal like crazy.
Right.
Can you calculate how?
I don't think that's been done yet,
Okay.
but we're probably not going to build new coal plants, and so a lot of this is also economics. There aren't.
I'm sorry, why won't we build new coal plants?
It's not economically viable to do so, right? It's not just that we're worried about the planet in the future. It makes no sense for anyone to do that at this point. And the whole argument of, we're going to dig up more coal, no one wants to buy it. So, so we
You're
may,
preaching to the choir here.
Yeah, I know. Well, that's
Sanjay and Yury, yeah.
Well, I think we have 4 years to pull out of the Paris, and there's another election.
You know what I
before that.
discovered
Right.
is, and this is important, you can applaud. If I am correct, and I don't think they thought this through, by invoking it when they did and how it was, the actual date in which it would take effect is November 4th, the day after the next election. So that would focus the mind, as Dr. Johnson would say, right?
Right.
And I think actually this is fundamentally wrong, not because there are not that many other countries that are out, as you can see from this map. I think it's about economic competitiveness. Simply, countries that are investing now in novel, modern technologies, solar, wind, which pretty much can provide almost free energy. At the time they become dominating those sources, those countries will have energy superiority and basically govern the world. You can look back, for example, at South America, which was very successful agricultural part of the world after the Second World War, richer, more prosperous than others. But they were enjoying their prosperity without building modern industries. And countries which were destroyed, like Japan, really in shambles, in ruins, they decided, okay, we cannot go the same way. We need to do something different. For example, they completely changed all traditional ceramics industry from pottery to electronic ceramics. They become the leading country in electronics.
And so the
Very
way we
rich.
would do it, to get back to the main topic here, is through new materials. For you, what is the holy grail of new materials?
I don't.
Yury's Maxine.
Maxine?
Well, again,
I can
yes.
say it. He can't say
Maxine,
it.
by the
Yeah,
way,
yeah.
is spelled not as in the bistro on the Upper East Side. It's spelled
No,
M-A-X-E-N-E.
it's spelled MX in like graphene, the same suffix here.
Yeah.
But yes, Maxines were just on the cover of Chemical and Engineering News, and this is a
That's
magazine
not the
of
one
the
that you
American.
two edit, right?
Pardon?
That's not the.
No.
Okay, I thought maybe you
It's a
put
sister.
yourself on
It's
the
a sister.
cover.
No.
Yeah, we used to do that.
We
at
would do
time,
that.
yeah.
Yeah.
This journal, the American Chemical Society, that goes among the 150,000 subscribers and members here. It's just one of these exciting new materials.
And why is it? It's an improvement on
Because-
graphene. Or?
Right. It's a more conducting than graphene. It's actually more transparent than graphene in thin layers. You can make transparent conducting screens for cell phones, TVs.
And is that also for transmission of electricity?
Yes, because when you transmit electricity, high is resistance, more you lose. More electricity you transform to heat. That's why you charge your battery, it produces heat. You want to charge it in 5 minutes, you get a very, very efficient heater. But you store very little energy as electricity. You have highly conducting material like Maxine, you can do it better. Moreover, what is important? There are some exciting new nanomaterials which are produced in nano quantities. And this may be good for very small electronic device. But if we need to build batteries, we need larger quantities. Maxine is a scalable technology.
What about for wearables?
Well, this is another application. We need large amounts of energy for replacing coal. But I already talked about collecting electricity, static electricity. Paul mentioned piezoelectric systems. For example, you can buy shoes that will lighten up as you walk here. Fine. But you can store this energy and really transform your clothes into your devices. You don't need them to carry a smartphone. We went from desktop computer to laptops to smartphones. Next will be, it can be embedded in your jacket, in your sweatshirt. Your sweatshirt can be cooling or heating your body depending on the temperature outside. Mm-hmm. It can collect signal, temperature of the body, pulse, and send actually signal to your doctor in case of medical emergency. And this is what we are trying to do. And for this, we need, again, low-dimensional materials, nanotube, graphene, Maxine, that will provide circuitry built into our clothes. And that's why, again, this new materials...
almost like a semiconductor was to creating a new industry, this could do.
Exactly, this new Internet of Things.
And there are more materials to discover. This is a recent discovery in Yury's lab that's gotten very far very quickly. But we're just
your lab?
Yes, this is a discovery at Drexel. We produced about 30 of these new materials so far. We did, in collaboration with scientists from Singapore, high-throughput calculation going on more than 1 million possible compositions. So really, we can discover materials. Moreover, we can computationally design them. And they try to make materials with properties we need to make either faster battery or split water using sunlight more efficiently. And this is, I think, what much of the nanotechnology
But it does
is
remind
about.
me of 70 years ago when they finally figured out how to make silicon into a semiconducting and deal with the surface state, all done through government funding of basic science. Are you worried that you're going to be hurt if the government of the United States, compared to China, which is escalating its funding of basic science, are we in jeopardy?
yeah, we're risking our future.
Just that simple. Thank you.
I agree with Paul.
Sanjay, big new breakthroughs on batteries. I know you're working on some. And what are you doing in New York to implement a new battery idea?
Well, of course, we'd like to use Yury's new materials.
That's why we're getting you together.
But in the meantime, we are using some of these materials like carbon nanotubes to provide pathways for electrons to get them out. One of the things that we've done is spun off a company which tries to capitalize on zinc, which has 2 electrons, and manganese dioxide. I mean, you know them in your Duracell batteries, but they aren't rechargeable, of course, so to make it rechargeable. And the primary use is to support renewables at a very low cost. In order to make a battery which can be used for this purpose, you need the cost down to about the cost of pumped hydro, which is roughly 2 cents a kilowatt hour. That's an incredibly difficult target for a storage system.
Are you collaborating with the local utilities to help do that?
Con Edison, mainly. So there'll be an installation shortly in Brooklyn, and there's one in Borough of Manhattan Community College. And yeah, so the idea is to capitalize on nanomaterials like carbon nanotubes to access the full two electron capacity, 2 electron discharge capacity of manganese dioxide. There's 2 electrons there as well, as you know. Right, so which is quite a trick, again, because it's not easy to do.
So you're doing that in a new battery technology that might be part of a test grid in New York as a collaboration with Con Ed?
Yes. So
Now, let me go back to the question, because Paul answered that he didn't worry too much, or you do worry about pulling out of Paris, but you think a mitigating fact will be a whole lot of us won't pull out of Paris. Do you worry or see any signs at all that your push to do cool new things like that might slow down, that utility companies might say, hey, we don't need to be doing that as much?
Well, Con Edison isn't doing it because of solar. They're doing it to relieve congestion so they don't have to build another substation. So it's a different use. There are many reasons for storage, and one is to use capital more efficiently. You've got generating capacity, which, during peak hours, you can't overbuild capacity just to supply the peak. So what you do is, if you can store it, then you supply the peak hours out of storage instead of overbuilding generation or transmission distribution systems. So the whole idea.
Let me remind everybody, because I'm now looking at our Twitter feed. It's hashtag WSF, right? 17. And we're opening up for questions soon. So if you want to tweet one, or if you can find somebody else to tweet it for you, if you don't have a phone. But everybody said they had phones. So anyway, let me ask, this is somewhat controversial. I mean, we're loving to hear what you have to say. But there are people who feel it's controversial to think that we can engineer our way out of the climate change crisis. That instead we should be reducing our use of fuels, we should be stopping all fossil fuel use, and that somehow trying to mitigate the carbon problem by inventing new technologies, there's been some resistance to that.
Well, it's all part of one big equation. As we said, there's producing the energy, and we have ways to do that reduce the amount of carbon we produce. There's storage that we can use, and then there's efficiency. And Nano has a role to play in all of those. And as you saw, we have to go into deep dives in terms of the science and engineering on the one hand, but then, like a chess game, look several steps ahead to see where they might go. And that's not just economics and policy. It's, as you brought up, safety, manufacturability, as Yury mentioned. There are a lot of things that have to happen between innovations in our laboratory, but all of those areas can be affected by what we do. So I would say, we can innovate and engineer as part of the solution, and another part of the solution will be efficiency from the point of view of reducing what we do.
But suppose we could engineer so that we could use all the energy we wanted and all the fossil fuels we wanted and somehow engineer our way out of having a carbon issue in the atmosphere. Would that be a good thing?
Sure, why not? Right? If you produce less.
I get to ask the question.
Okay, sure, right.
No, I mean,
Right.
you've heard the pushback.
Right, but there's a significant time lag between what we're able to do now and what we'd like to be able to do. And so, hopefully there are multiple approaches that get us to where we need to be, some of which are technology and these innovations, and others are, what we do over the next 3 years.
Well, let me ask both of you, and I'll ask it in a different way. Is there some virtue in trying to cut back on our energy consumption, even if we engineer ways that energy consumption isn't as harmful to the environment?
Well, I think it's happening naturally. People are reducing their energy needs. You can just see that in the United States. Also, urbanization to some extent helps with that, because if you look at New York City,
Right.
in terms of the national picture, we consume a lot less electricity per capita.
And
being in
certainly
New York.
less
Yeah. In
gasoline or oil. Yeah.
For sure that. But I think also, if you see the most difficult problem is transportation in many ways, because you can control centralized carbon dioxide production, but everybody is driving around and producing carbon dioxide and other pollutants. That's the most difficult. So I think that transition, though, has to come probably from some form of electric vehicle. And that might happen quicker than we imagine.
Well, so let me use that as a springboard to ask each of you sort of a bigger concluding question. What radical game changers do you see? I guess I would ask specifically in transportation fuels, because that's the hardest, but some radical game changer that you could see happening 10 years from now, maybe 20, that would change the way we use and produce energy?
Yury's super fast charging supercapacitor or whatever.
But then we would have to go to an all-electric systems, right? That only works for batteries, right?
Well, but it impacts transportation.
What's
It
that?
impacts transportation hugely, if you could do that.
It can impact transportation, but there are also, I think there will be diversity in many ways. Let me just again take China as an example. They built a network of railroads connecting very fast railroads connecting all the big cities. So a lot of people who would travel by other means, flying, traveling by buses, now take these trains. There are supercapacitor buses that actually service public transportation. They cannot run on for 15 minutes, but they charge at every bus stop. And then supercapacitor can survive like 1 million cycles. They provide very convenient urban transportation. And there are regular electric cars and hybrid cars on the roads. So this is one of the ways slowly switch to electrically based technology here. I think it's really important, and this is going to happen. But for this, again, we need new materials. We need materials which are lighter. We need materials which can store energy. We need materials that can generate energy from sun and wind. And also, in many cases, to save what you mentioned here, if we have much better insulating materials, not for our clothes, but also for our houses, we will need less energy to heat them or cool them in summertime. So I think really with new generation of materials, we will be able to solve many of the current problems.
Yeah, I think to summarize, the answer isn't there's going to be one big jump and all our problems will go away. In fact, there will be many, many different approaches that'll each help in their own way. We'll come up with more efficient electronics, more efficient insulation, more efficient energy production, more efficient transmission and storage. And in all those ways, we have a possibility of chipping away at the amount of energy that we need, the amount of energy we use, and also how we make it.
Sanjay, the first question from the audience I'm going to throw to you, which is, do you see the dual carbon battery as a realistic opportunity for the industry?
I actually don't know exactly what the dual carbon battery is.
I won't call out the hashtag or the Twitter address of the person sending it, but I don't know if anybody there sent it. You want to explain?
Yeah.
All right. What are we going to do to increase the potential, or does anybody else want to take it?
Well, again, I think what is meant a battery with
Maybe he
cathode
knows,
and
yeah.
anode, people consider this design of materials where you just have carbon material. Because supercapacitor conventional is to a certain extent dual carbon battery, because you have carbon electrodes on both sides. The problem is that it doesn't store enough energy because it's electrostatic storage. You want to store it chemically by intercalation. The intercalation. So I think it's just one of the solutions. Is it the best one? No one knows. I think it's one of the designs of the battery people are playing in the lab at the moment. There is no breakthrough as far as I know yet.
Do you think carbon will still be a good base for the battery?
Carbon is actually, I think, has another important reason why to use it in batteries and everywhere. We're talking about burning fossil fuel. If you break, for example, natural gas, produce pure hydrogen that gives you water vapor, and produce solid carbon. This is a material to build off. Second, when you really need to get rid of it, even if you incinerate it, it doesn't produce much of a toxic residue beyond carbon dioxide. Right. So there are a lot of advantages of building things off carbon.
It's also light. So one of the ways we judge batteries is by how much energy per weight.
So it's an attractive solution, but we're not there yet.
Recent solar costs has fallen below the cost of coal and still using mostly non-nano-based tech. What would be the cost or what would be the efficiency of a solar panel that is engineered using nanotechnology? And I guess I'll simplify, but how can you use nanotech to really bring down the cost of solar panels?
So there are a number of different strategies for how to make solar cells. Some are incredibly expensive to make, and you'd only consider them for a satellite because what really matters is how much power you produce per weight. And you don't need those in your home. What you ultimately want is the limit is a paint, right? That's as efficient as it could possibly be in producing power, and everything else is somewhere in between. And so we could certainly imagine more than doubling the efficiency we have in current solar cells. And there's a wonderful chart.
Would do it. Yeah.
It would make a big difference. And we've seen those kind of rises over time. Again, the materials question comes up. There are commercial solar panels. They use different materials, and they all are priced to be the same per amount of power. But if people are interested, the National Renewable Energy Laboratory has a chart they constantly update with the record efficiency for each technology. And it's kind of fun to watch those efficiencies rise over time. And they do the tests. They don't. People send devices from all over the world to them to see how well
I'm going to get back on my hobby horse, but that's a government-funded lab.
It is indeed a government-funded.
And that would be cut in the potential budget.
I didn't read the budget.
Yes, it would be.
Okay, so
along with the National Science Foundation and everything else. So that would make maybe be almost as bad as pulling out of Paris is if you decide to cut all research funding and testing in the United States.
Right.
Okay. We have somebody actually watching on the live stream. I won't give his full name. Simon, of all the issues discussed tonight, what are the biggest roadblocks to a better energy future based on nanotechnology? Are they technological, or they become political now, the roadblocks?
I think there are many technological roadblocks, but many of them can be removed with the right policy, with support for research and development in introduction of new technologies here. So I think we can develop the best possible technologies in university and labs, but if there is no support to commercialization introduction, little will happen, at least not in the US. At the same time, just policy without existing technologies, if tomorrow government tell us, guys, make a battery that is 99% efficient, lives for 5 million cycles, and at cost of storage of penny per megawatt, we don't have a technology as well. So I think those things need to go really hand by hand together.
The United States isn't the only place in the world working on these projects. It just will give up our efforts and, in some areas, leadership in the field and the technologies that we developed elsewhere, and will later be buying them.
I have a friend who actually came from Twitter, Jack, I won't give the full name, but somebody I know and respect in this industry. How do we radically bring down the cost of high-quality, single-layer graphene production? That's in your wheelhouse.
I think this is a use. You have seen a chart for lithium-ion batteries. I paid, when I needed to replace a lithium-ion battery in Europe for my computer about a decade ago, more than $200. Nowadays, you can buy a computer for about the same price with a battery inside. Carbon nanotubes used to be extremely expensive. Now, Sanjoy was talking about low-cost energy storage, and they're using carbon nanotubes there. So I think it's an economy of scale to a very large extent.
And for the very last, we have 1 minute left. You just mentioned, Paul, that other countries are doing it. What is the likelihood that China and other countries will be the leaders in energy technology and not the United States based on the way things are going?
Well, there's already more investment there, I believe, and increasing over time. The production of solar cells is largely there, and in different areas and different materials, different laboratories and companies have shots at leadership. And so
you're about to go to India. Oh, you just came, yeah.
Right. Well, I think that China is more likely to be where there will be breakthroughs, but you can never know where there's going to be a breakthrough. Throwing money at a problem doesn't necessarily, make for a breakthrough. It doesn't hurt, but some of the strangest things happen where there's almost no money thrown at it. And somebody once came to me and said, we'll give you lots of money to make a substitute for cobalt in the lithium battery. And I told him that told them, because it's a big company, that it can't be guaranteed. So the amount of money you put in doesn't really matter. It's going
Final
to take
word,
time.
Yury?
I think in reality, technologies develop elsewhere, basic science done elsewhere, to a very large extent become consumed and used in all the world. Yes, I wish we would have leadership in this country, but we will benefit from technologies developed in other countries. At the same time, for economic prosperity of us, our children living here, we need to stay leaders in technology. Otherwise, the things, as I gave an example of South America, can happen when countries that misses an opportunity get thrown back. I don't know whether it will take a shock, like, for example, Soviets putting Sputnik on the orbit to make a major change, or just next election. But I think things need to be changed to keep the US at the cutting edge of energy technology in particular, and technology in general.
And I do think that it's a question of being both leaders in technology and leaders in policy, because one of the things you've all said tonight is those are woven together. Paul, Yury, Sanjay, thank you all very much.
Thank you.
Great, very good.